So hello, everyone. As most of you know, my name is Eric Kazyak. I am currently a postdoctoral fellow at the University of Michigan. I work in the Dasgupta Research Group. And for the last, almost 7 years now, I've pretty much been eating, sleeping, and breathing batteries and other energy-related technologies, but mostly batteries, really. And so today I'm really excited to tell you guys what I've learned over the past 7 years, some of the work that I've done, and really how I see the state of battery technology as it pertains to climate change and renewable energy technology. And hopefully the most interesting part of this will be kind of the forward-looking part, where we're headed based on that. So before I get into this too far, I'd always like to thank everybody that I work with. I'm not working in a vacuum. I learn from other people and work with other people. So my entire research group, like I said, the Dasgupta Research Group at the University of Michigan, and a bunch of my collaborators, Jeff Sakamoto and Don Siegel, both also do a lot of work on batteries, and then two now postdocs as well, one at MIT and one at Cornell, Mike Wang and Regina Garcia Mendez. And of course, all of our sponsors, both government and industry sponsors that enable us to do some battery research. And I'll just say up front, those past 7 years, I've been mostly talking to people that also have been working on batteries for 7 years. So if at any point I say something, an acronym or anything that you don't understand, please stop me. I don't want to be rambling on and not have this be useful to anyone. So at any point, if I accidentally weave in some jargon, that was not intentional, and please stop me and have me clarify, because I'm sure you're not the only one that it's not understanding it. So yeah, so I'll start kind of with some context. Most of you are probably familiar with charts that look a lot like this. And as it pertains to batteries, I wanted to point out just a few things. We really probably could spend the whole night talking about just this chart and really glean a lot of useful information from it. But I want to point out just a couple of things. One, that currently and still over 3/4 of the total energy used in the United States comes from fossil fuels. Two, over 2/3 of that energy is currently wasted. It's rejected energy. It's not going to services. Three, of the cleaner sources, solar, wind, hydroelectric, etc., almost 100% of that energy goes directly to electricity generation. And in contrast, if we look at the transportation sector down here, then almost 100% of that comes from fossil fuels, and almost 100% of that is in the form of petroleum. So if we're going to move away from these fossil fuels, then we need to increase the amount of the renewables, of course. And one of the problems that often comes up as it pertains to renewables is the intermittency or non-dispatchability of solar and wind energy. That basically means that at certain times of the day, you're producing more energy than others. So in order to have a grid that is predominantly supplied by these intermittent sources, you inherently have to have storage built in so that you can store energy when you have excess production, when it's windy or sunny, and then you can get that energy back later when it's not windy or sunny. And secondly, we need to replace, in addition to electricity, we have to replace the fuels that we burn for transportation. We like gasoline and diesel fuel because they're very dense forms of energy that can be used on demand. So if we're going to replace that, then we need something that is also energy dense and can be used on demand. So just kind of to wrap up, energy storage is really vital for two things as I see it. One, decarbonization of the transportation sector, and two, enabling widespread implementation of these intermittent renewable sources. So what are our choices here? Well, as I see it, we have three. One being hydrogen fuel cell electric vehicles, where we're basically doing a cold combustion process, combining hydrogen gas with oxygen gas to form water. So the emissions are great, just water and electricity. The second option would be battery electric vehicles. That'll be the focus of most of this talk. And the third option would be bio-derived fuels or biofuels, which would be the option of basically growing a plant or algae that uptakes CO2 and then processing it in some way to make a combustible fuel, and then burning it. And basically that can be made to be quasi-carbon neutral because the CO2 emissions were uptaken at the beginning. The problem is the current technology has a relatively low energy return on investment. So the amount of energy that you have to put in order to, cultivate the crops, harvest them, and process them is almost as much as you get at the end. So the return on investment is not that high. There are alternatives out there that are better, but they're really not ready for a large scale at this point. And there's also some land use implications with biofuels, notably that if we're using land to grow crops for energy, that is land that probably could be used to grow crops for food, which has a whole host of social justice implications for it. And then it could also drive things like deforestation. So in my opinion, while biofuels probably do have a role, they're better suited to applications that are more difficult to electrify via these other two options, such as aviation and things like that. So, okay, we're down to two options, battery electric or hydrogen fuel cells. So let's take a look at kind of the energy flow for these two technologies. One, for battery electric, we have energy from the grid. We have to transport it and get it to where you need to charge a battery, which has some inherent losses. It might be around 80% efficient. And then the actual end use, the charging the battery and discharging the battery to drive an electric engine is extremely efficient. It can be made to be over 90% efficient. In contrast with like an internal combustion engine that might be only 20% efficient at the same process. So battery electrics have a big plus there. In contrast, hydrogen fuel cells, which hydrogen is not a fuel that we can just go and mine. You either have to use electricity to split water and make hydrogen, or you can use high temperatures to split hydrogen off of methane, but that's not a carbon or a low carbon option. So we'll assume that you're starting with the same electricity, preferably from wind or solar, and you have to make the hydrogen with electrolysis, compress it, transport it, and then you can run your fuel cell to generate electricity. And at the end, you then need a battery again because it's not practical to have a fuel cell big enough to accelerate a vehicle quickly. And there's losses at every state along the way there. So the overall efficiency for a hydrogen fuel cell is only about 30%, maybe not even that high. So what this means in the end is that if we wanted to have a hydrogen-based economy, we'd need more than twice as many wind and solar farms to supply the electricity, which really doesn't seem to make a lot of sense. So for that reason, and I hope I've convinced you, battery electric vehicles really are the most promising means to reduce the carbon intensity of the transportation sector, which is responsible for nearly 30% of the overall greenhouse gas emissions in the world. Now, what about grid storage? I mentioned at the beginning, there's these two big things, transportation and enabling renewables on the grid, which they're not isolated, you need both. But for grid storage currently, we only have about 2% of the total generating capacity. This is worldwide, and actually it's about the same in the United States. And almost 100%, it's above 95% of that storage capacity is pumped storage hydro, which there's a schematic here where basically when you have surplus energy, you pump water up a hill, and then when you need more energy than you're producing, then you let the water flow back down and you produce electricity from the standard hydroelectric pathway. The problem with this is that it's geographically constrained. You have to have a body of water at the bottom and the top of a hill, a relatively large hill, and it has to be pretty close to a population center so you don't have to transport the energy too far. And because of this, we've kind of saturated most of the good places to do this, and it's really seen pretty limited growth in the last 2 decades plus. In contrast, if we look at the balance of this, that less than 5% of the total grid storage right now, what's becoming more prevalent is batteries, whether it's flow batteries, lithium-ion batteries, and a few other options such as flywheels and compressed air. But this is a battery talk, so I'm going to focus in on the batteries. And if we look at just the lithium-ion battery, this is the implementation of lithium-ion batteries and other battery options, but it's dominated by lithium-ion over 90%, the energy capacity for grid storage installed each year over the last 15 or so years. And what you see is that in the past 5 years, especially, the implementation of lithium-ion batteries for grid storage has really skyrocketed. And the reason for this is that the price of lithium-ion batteries has really, really dropped over those same years. And this is largely driven by the demand for lithium-ion batteries and low-cost lithium-ion batteries, which is predominantly due to electric vehicles. The scaling up of lithium-ion battery production, combined with a few other things, but it's really just an economy of scale thing and getting the entire supply chain in order. The price of lithium-ion batteries has come down from, almost $700 per kilowatt hour. And just to, everyone probably knows this, kilowatt hour is how you pay your electricity bill. You probably pay somewhere between 10 and 20 cents per kilowatt hour. So this is not a huge amount of electricity. You need quite a few kilowatt hours, somewhere between 50 and 75 probably for an electric vehicle. But the fact that the cost per kilowatt hour, and this is at the pack level, the full stack here, so not just the individual cell, but everything you need in order to put this battery inside of an electric vehicle, has dropped, and we're approaching $100 per kilowatt hour. And in fact, some producers can meet less than $100 per kilowatt hour. And really, we're right at what most people projected would be the tipping point where electric vehicles would really, really start to take off because they become cost competitive. So I just want to point out, though there are other options for grid storage, currently lithium-ion batteries are the leading option. And the fact that they are also the leading option for electric vehicles, and since EVs dominate the demand, they will dictate the progress in technology, and they will dictate the cost coming down. So they're coupled together. And in fact, beyond that, old technologies that are no longer good enough for EVs will become the low-cost option for grid storage, and batteries can have a second life. So for an electric vehicle application, you might call your battery not good enough anymore if you can only drive 80% as far as you could when the car was new. But for grid storage applications, if you can buy the battery for half the cost, that still makes sense, and you can more carefully control the charging rate and discharging rate and things like that. So these things go together, and that's why I'm going to spend most of the rest of the time here talking just about electric vehicles, because, as I said, they're coupled. So I hope so far I've convinced you why we care about batteries, and I just want to take a second. Does anyone have any questions?
Is it Eric?
Yes.
I'm just curious. You mentioned about the pumped hydro. There are other gravity-based solutions. I've seen things with using train tracks and lifting weights, using mine shafts and lifting elevator type systems. Have you looked? I'm just curious if those gotten much traction, or
so those would fall into like a mechanical based storage, or like you said, gravity. There definitely are. So flywheels are a related technology. That's basically where you get a very heavy disc and spin it really fast in a vacuum so that there's low friction. You use magnets to levitate it like a maglev train. And they each have kind of their own role to play because they have different properties. So pumped storage hydro has been the best, or the dominant one because it's really cheap if you have the right place to do it, and you can discharge for a very long time if you have a very large reservoir. Whereas lithium-ion batteries, now at least, are more economically viable for the short discharge time. So if you have a short window, so they're used more for load leveling, frequency regulation, things of that nature, rather than kind of filling in the whole trough of a nighttime lull in production or things like that. I don't know the specifics, like what breakdown in the last couple of years those gravity methods have been, but I do know that lithium-ion and other types of batteries, I shouldn't neglect the fact that there are some really exciting new like flow battery systems where you really can decouple the energy and power requirements, and they can be made very low cost because you don't care about how much it weighs. So there are lots of other options here, but in the past few years, lithium-ion batteries, because of the economics, have really started to dominate this space right now. There are going to be other contenders moving forward, and I think it's a all of the above type situation. We need a lot more storage than we have now if we're going to scale up wind and solar like we need to.
Thank you.
Yeah.
Could you explain what you mean by rejected energy?
Sure. So any transfer of energy from a thermodynamic standpoint is not, it can't be 100% efficient. So anytime we're taking, gasoline and burning it, almost all of that energy is lost to heat and sound rather than going into, moving us or the stuff that we need to move, or in any of these situations, right? So,
so it's the energy that doesn't perform work.
Right. It's the stuff that's not doing stuff that we wanted it to do. Right. So it's wasted. So there's a huge opportunity here for efficiency improvements, of course, and moving to more, moving away from burning things is always good for that, because heat is the lowest, well, pretty much the lowest quality of energy that you can have, whereas electrical energy is very high quality energy. We can use it very, very efficiently. So that's another benefit of going to a more electricity-based system rather than using combustion, because you can be inherently more efficient as well. Does that answer the question?
Yep, thanks.
Not a problem. Any other comments before I really dive into some more technology stuff, how things work as far as batteries, ways to make them better, and the outlook moving forward? All right. So next we're going to talk about the working principles of lithium-ion batteries, what kind of the recent progress and outlook for lithium-ion is, and then we'll go beyond lithium-ion, looking at some next generation technologies, and talk about kind of where that's going to take us. So this is an old plot. This is from 2001, but I think it's worth looking at. Actually, I just realized this today. So we all know lead acid batteries. They're cheap and do what we need them to do in a lot of cases, but their energy density, which is how much energy you can store either per space. So the y-axis here is a volumetric energy density, so watt hours per liter, or per mass. On the x-axis here is watt hours per kilogram. Because lead is so heavy, you can't store very much energy per weight. So that's why your car battery is so heavy. In contrast, now what we're using is lithium-ion batteries, which we can have much higher energy density, which is really what we care about for transportation, because you have to carry your energy source around with you. So if you're going to have a lot of it, it needs to not weigh too much or be too big. But what I found out or noticed today was that, this is 20 years ago. Actually, the lithium-ion batteries that we make today can do significantly better than these authors projected, because of some really exciting advances that have happened over the past 10 years. And I'll also point out that this will come back to this unsafe lithium metal bubble, because that might be the future. And it won't be unsafe. All right. So I just want to make sure everybody's on the same page, so I'm just going to take a step back here. So this is how lithium-ion batteries work. All batteries really work in generally the same way. So here, a battery is made up of two electrodes, a positive electrode, or the cathode here, and a negative electrode, or the anode. And essentially, you're storing chemical energy in the form of chemical bonds. So, when a chemical reaction occurs, you can release energy in the form of heat. But in an electrochemical reaction, like is happening inside of the battery, we actually split that chemical reaction into two half reactions. And what that enables us to do is to generate electricity rather than just heat. And like I said a moment ago, electricity is a much higher quality of energy. So this can be almost 100% efficient process. And what enables us to do this is we're separating the two electrodes out in space, and in between you have an electrolyte that only transports ions, in this case lithium ions, back and forth, and then the electrons are forced to go through this external circuit in order to reunite with the lithium ion on the other side. And in that external circuit, we can do useful work. And really, we can think about this system as these two electrodes as two sponges with water in them, one at a higher vertical position than the other, so is higher up. And as we all know, systems in nature like to minimize their potential energy. So if you have a ball at the top of a hill, it's going to roll down to minimize its potential energy. Similarly, the water in a sponge, if you squeeze it out, will flow downhill from the negative to the positive. And it's a little bit confusing. The negative is higher than the positive because electrons are negatively charged. So a higher energy state for an electron is a negative charge. But essentially, if this is an analogy to a battery, the voltage output of the battery is equivalent to the difference in height. So, and then the capacity of the battery would be the amount of water in the sponge. And the amount of energy that you can get from a battery is essentially is a product of the capacity of the battery and the voltage at which it can output. And that's linked to the energy states of the lithium ions and electrons inside of these two electrodes. So you have one electrode that the lithium ions really don't want to be in, and another electrode that they really do want to be in, and that's where your voltage comes from. And these, like I said, are electrochemical reactions, and in this case, they've been very precisely engineered so that they're controlled and that they can be reversed. So the important thing is that whatever discharge process happens, it doesn't damage the electrodes too much to the point where you can't reverse things and put everything back where it was. And essentially that's what you're doing when you're charging. You apply a voltage when you charge, and that essentially tilts the whole table, if you will. It tilts the energy landscape and drives the current or the water back the other direction. So like I said, the voltage is the difference between the two materials on each side. So then when we're making a battery, we have to select two materials, one for the negative electrode. So those materials are shown here on the bottom. Those are at low potentials versus this lithium plus, which is basically where a lithium ion will become a lithium metal. It'll accept its electron back at 0 volts. And then your positive electrode materials up here include lots of these mixed metal oxides. So it's like lithium and manganese and maybe nickel and oxygen. And because lithium really wants to give up its electron and oxygen really wants to gain extra electrons, that's why lithium really likes to be in these materials, because they're oxides, and lithium really doesn't like to be in most of these materials down here because there's not oxygen around to accept that free electron on lithium. So today's lithium-ion batteries utilize, without exception pretty much, graphite negative electrodes. And there's a lot of reasons for this, but the biggest one is that it's very reversible. You can put lithium in and pull it out because it's layered. So the reason why, we can use graphite in our pencils is because it's got this layered structure, and those layers can come off. Well, in the case of an electrode, we can actually shove lithium ions in between the layers and then pull them out without damaging the graphite structure too much. And we can put a lot of lithium in relatively. Whereas the positive electrode materials, there's a whole bunch of different ones. I'm not going to get into specifics there right now, but I will point out that, so we're using graphite right here. That lithium metal, which was the highest point on the plot of the different types of battery, is all the way out here. So it's around 10 times as much lithium much capacity per kilogram of lithium as graphite is. So if you could make lithium metal work, pure lithium, there's a big upside here versus graphite. So once we've selected these materials, then basically we grind it up into a small powder, and then we mix it in what is basically just a giant KitchenAid mixer here. So you can see that gray stuff in there is the slurry. And then essentially we paint that onto a very thin metal foil. The electrode is about as thick as a strand of human hair, give or take. And then we cut out individual electrodes from that large foil, and then stack those electrodes, anode, cathode, with separator in between so that the electrodes don't touch. And then you put a liquid electrolyte in there, seal it up, and you're good to go. But if you look at kind of the stack, it looks something like this, where you can see the metal foils here. So you have an aluminum foil on the positive electrode side, you have a copper foil on the negative electrode side, and then you have a polymer separator that spaces them out. But this is porous like a sponge. So the liquid electrolyte that fills all of the pore space in this whole structure can permeate through the separator and into the electrodes. So then when you connect your light bulb or whatever you're going to power to these current collectors, you have a voltage and you can do useful work. If you have a cell that's a cylinder, like kind of looks like a AA, this is the form factor that, say, Tesla uses, then rather than these flat sheets, you have a jelly roll basically wound into a spiral, but the same basic structure as this, just kind of wound up. Any questions about that? All right. If not, this is just a kind of a closer look. You can really see how these electrodes are actually made up of little tiny particles on the order of maybe 10 microns or so, 10 micrometers. That is very small. And that allows the electrolyte to get in there, the ions can get in. So essentially, we have graphite and then some mixed metal oxide on the positive electrode. And that has gotten us to where we are now, which is a volumetric energy density somewhere 300 to 600 watt hours per liter, gravimetric 200 to 260 watt hours per kilogram. The reason, or one of the biggest reasons we really like lithium ion beyond the energy density, is the fact that it can be cycled extremely efficiently. And this isn't energy efficiency, this is Coulombic efficiency. So this is, if you send 1,000 lithium ions from one side to the other, or actually if you send 10,000 lithium ions from one side of the battery to the other, you can get 9,999 of them back in most cases, which means that you can cycle them back and forth and back and forth and back and forth well over 1,000 times, sometimes up to 5,000 times. So, if you put that into context, if you have a battery electric vehicle that has a 300-mile range, if you cycle that 1,000 times, that's a 300,000 mile life of the vehicle. If you cycle it 5,000 times, you're getting ridiculous numbers of miles. So the battery would last well longer than the car would at that point in most cases. And the cost, like I said, it's coming down somewhere just above $100 per kilowatt hour. So how can we make this better? What does a better battery mean? And we all kind of know this instinctively because we use batteries every day in our laptops and phones. But what do we want? We want to be able to charge it really quickly because, even if it's a phone, if your phone's about to die, you need to plug it in and get it back up so you can use it the rest of the day. Or if it's an electric vehicle and you're on a long trip, you don't want to have to stop for 4 hours in order to be able to drive another 100 miles. You want to stop for 10 or 15 minutes, grab some coffee, get a burger, whatever, and then be back on the road and be able to drive another couple 100 miles, preferably. And we want our battery powered vehicle also to be able to drive a long way and not be like 50% battery in the back seat and not have leg room or anything like that. So we need our batteries to store a lot of energy in a small space so that we can have a long range vehicle. We don't want them to catch on fire spontaneously, or if you get in an accident, or if you charge it wrong. We want it to be inherently safe and stable. We want to be able to use it if it's, minus 20 degrees outside or 120 degrees outside. We don't want to have to worry about that. We want it to last an extremely large number of cycles or be able to sit on the shelf. We don't want to park our car in the parking lot when we're on a trip around the world or something and come back and the car's dead because it's been sitting there too long. That's not acceptable. And we don't want it to cost an arm and a leg, right? Okay, so first I'm going to look at fast charging here and try to go a little faster because I like to talk apparently. So what limits fast charging performance in lithium-ion batteries? Well, it turns out that it's mostly related to the anode, the graphite. And to explain what happens during fast charging, I need to take a step back and just explain what happens during charging period. So when we put graphite, which is a layered material. That's what these little lines in here represent, into the electrolyte. That's what these lithium ions with the red things represent. And we start putting lithium ions into the graphite. The first few lithium ions are like, oh, this is cool, there's plenty of room. And then it starts to get crowded. And when that happens, the energy level of this electrode raises up, which is good because that's storing energy if we're putting things into a higher energy level, because then they're going to drop a long way and we'll be able to do a lot of work. But materials are not just stable at any energy level. So at a certain point, if the electrolyte has unoccupied states that electrons can go into, that will happen. So then the electrons, instead of recombining with the lithium inside the graphite, will actually reduce the electrolyte itself. It will react. So it'll consume the electrolyte and form a reaction layer on the surface. And actually, it turns out this is the only reason why lithium-ion batteries work at all. If this didn't happen, if this didn't form a passivating shell that protected the graphite from further reaction, you wouldn't even be able to discharge the battery once, let alone 10,000 times. But so then we're left with this structure, the graphite in the middle, and then this, what we call SEI, which is a solid electrolyte interphase on the outside. This is the magic that makes a lithium-ion battery work. And it was a serendipitous discovery. It wasn't designed this way, it just worked, which is really remarkable. But if we try to charge this too fast, essentially we can't put the lithium ions in fast enough, so they stack up and you form this concentration gradient across this porous structure. So you have more lithium ions at the surface of the graphite than deep in here. So then when you're charging your battery quickly, you're preferentially charging the surface of the graphite, and eventually the lithium ions stack up, the surface of the graphite gets totally full and crowded, and rather than just sit around, the lithium ions actually plate out as metallic lithium, and they form what's called a dendrite on the surface of the graphite. But now this is no longer protected by that passivation shell, so then it continues to grow, it forms more SEI on top of the lithium metal, which again consumes liquid electrolyte, and you only have a finite amount. And because lithium metal is so reactive, we can't actually strip all of it back when we discharge our battery. So you get these isolated little pockets of lithium that we call dead lithium, and that's directly reducing the capacity of your battery. And what that causes, this is trying to charge a state-of-the-art high energy density battery in 15 minutes, from almost 0 to 100% state of charge. The capacity of the battery fades very quickly. So we often use 80% retention as a failure mechanism. So here it only lasted 12 cycles. And that's because you built up this thick layer of dead lithium on the surface that you can't get back, and it blocks further charging. So this is one of a couple slides where I'm going to show something that my group did. So I have a manuscript under review right now where we developed an artificial SEI. So it's that interphase shell. So we deposited a coating there rather than letting it happen naturally. And our engineered version performs much better. And as a result, we can charge our batteries quickly without them fading. So here, rather than 12 cycles, our battery lasted to 80% more than 500 cycles. And then another approach here that we developed last year is basically using a laser to cut holes to allow the lithium ions to get deeper into the electrode. And that works even better. We can even go to 10-minute charge and still have 90% capacity after 500 cycles. And this is really a game changer for electric vehicles because of the fact that it alleviates range anxiety. And just kind of showing you here, rather than this thick layer of dead lithium, there's just a little bit sprinkled here and almost nothing on what we call this highly ordered laser patterned electrode or whole electrode. Yeah. So that's kind of a shout out to our group's work in this space. There are other approaches as well, but I really think fast charging is a problem that we're, as a community, we're pretty close to overcoming in these electric vehicle style batteries. Any questions here?
Yeah, I'll put in a question. This is Patty. Missed your first part because I was having technical difficulties. But anyways, I have a Bolt EV,
Yes.
And I got it in the first year that it came out, which was 2017. So of course they have the recall on the battery. So they put a program in so I cannot charge. It's 80% blocked on my charging. But I do have the supercharger capacity. So I don't know what their battery does, but talking about 10 to 15 minutes, I did do some long distance travel with my car. And you have, back in 2017, you had to really plan things out to be able to do that, because unlike Tesla, there's just was not a lot of charging stations. So, and then looking for the superchargers. But even with the supercharge, by the time I would roll in there, it was a 45-minute wait to get that back up to enough that I could go another 100 and some odd, 150 miles or whatever. And I mean, I would sometimes get 300 miles on my Bolt. And when I didn't use a whole lot of energy, other stuff like air conditioning and things like that. I love my car, and I really think it is the wave of the future. But yeah, I'm looking for some kind of, we've got to work on getting this so you're not spending 45 minutes to charge your battery to get going again.
Yeah. That's exactly right. And the reason why, it's not that your car battery couldn't be charged in 15 minutes once. It's that it would be this orange curve, right? If you did it, 50 times, your battery, you'd only get 200 miles of range instead of 300 potentially, right? So that's the problem, is you get this lithium plating. So then Chevy has said, okay, we're just not going to let you charge it that fast, because we're not going to let this happen. It's also a safety risk because you have this metallic lithium around, but they don't want your battery to fade like that, because then they'll have to replace it on warranty or whatever. So they limit it. And that's why I think these types of technologies are really promising. So neither of these, so the whole or this artificial SEI, they actually don't reduce the energy density of the battery at all. They just increase the charging time, or decrease the charging time by increasing the charging rate. That allow.
For time reasons, we should probably move ahead.
Yep.
And maybe save the rest of the questions until the end.
Okay. Yeah, I'll go quick through the last part. That's fine. Cool. So moving on. So then there's still a lot of work being done on the lithium-ion batteries, whether it's changing to different cathodes. The big push here is to move away from cobalt-based batteries, because cobalt of Congo produces almost 20 times more cobalt than any other country in the world, and it produces over 70% of the cobalt that is produced in the world. So then it has a lot of social implications to have a lot of cobalt in batteries. So we're really trying to move away. And in the past 5 to 10 years, we've gone from a 1-to-1-to-1 ratio of cobalt in this most common cathode called NMC to now 8-to-1-to-1. So we've dramatically reduced the amount of cobalt, which is really good. Now we're trying to mix in some silicon into the graphite, because you can put a lot more lithium into silicon. The problem is when you put so much in, it expands and then pulverizes itself. So it can't withstand the expansion, but that is definitely something that's happening right now. And then you can do some things at the system level, go thicker electrodes and thinner everything else, so that all of your mass and space is the stuff where you're actually storing energy. But that leads to poor rate performance, because those lithium ions can't get through that really thick electrode. And a lot of the other things like the separator are already pretty optimized. And if you try to go further, you risk safety concerns. Like the Samsung Galaxy Note fires were caused, in part at least, because they really tried to push the thickness of the separator down. It's only 4 microns thick, whereas the state of the art is more like 8 or 9. So it's like half, and it caused problems. So this is kind of where we're at. So the Tesla Model 3, it's around 250 watt hours per kilogram, depending where you look. Chevy Bolt is just a little bit behind that. That's because the Chevy Bolt uses NMC and the Tesla uses NCA. NCA is a little bit higher capacity, but has some stability issues. So Tesla's making a choice there. By mixing in some silicon, we can increase the energy density pretty substantially, but really there's not a pathway to push lithium ion beyond 300 watt hours per kilogram, or at least not much beyond. But if we switch the negative electrode to lithium metal instead of graphite, there's a path to much higher, 400, 500 watt hours per kilogram, which would be a game changer. So while there's incremental improvements left for lithium-ion battery, lithium metal could really be this disruptive step change. But there's a reason why we haven't actually gone to lithium metal. So this is a video that I took of a lithium metal electrode a few years ago. And what you see is that lithium metal doesn't like to plate out nice and evenly. It forms these dendrites. That was the reason why fast charging was a problem in graphite. But here we're trying to plate lithium metal, but trying to plate it uniformly. And again, you can't get it all back. It's low efficiency. And what that does is it kills your battery in a very short number of cycles, just 50 cycles or even less. Your capacity is going to drop to basically nothing. And if one of those dendrites happens to penetrate across that 10 micron thick separator, very, very thin, then you could get a short circuit and have some really big safety concerns. To be clear, this is not a dendrite caused fire. There was a short circuit in the charging system, but the effect could be similar if you have a flammable liquid electrolyte around. And the electrolytes that are currently used in lithium-ion batteries are these organic solvents that are very, very flammable. So if you do get a fire, it's going to be very problematic. But what if we could replace that liquid electrolyte and that porous separator with a solid material that was non-flammable? This would be great, right? But that solid material would have to do everything that the liquid does and the porous separator does, namely conducting lithium ions very, very quickly, not allowing electrons to go through, and to physically block the two electrodes from touching each other, all while being safe and stable for thousands of cycles and all of this. But if we can use solid electrolytes to enable the safe use of lithium metal, there's a really big upside, because maybe that solid electrolyte could make the lithium metal plate out uniformly, and then you can strip it back and cycle it safely. And that would give us dramatic improvements in safety, cycle life, and big one, energy density, as well as some pack level benefits, because there's a lot of weight and space and cost that's used to control the temperature of lithium-ion batteries. Because if they get too hot, you get thermal runaway and they catch on fire and blow up, basically. But if we don't have that possibility, because the electrolyte is now safe inherently, you don't need all that thermal management and packaging stuff, and you can make a big improvement. So this sounds like pie in the sky stuff, but actually last year, Samsung put out this really foundational paper in the solid state battery field that proved that you can make a pretty large solid state battery that has significantly better energy density than even Tesla's best. And this is, prototype scale, very frontier stuff. And they could cycle it, almost 1,000 times with very little fade in capacity. And this is with a lithium metal electrode. So indeed, these solid state lithium metal batteries can have very long life. And just for context again, we'd be talking, over 200,000 miles of life for an EV if it had a 300-mile range, roughly for 800 cycles. So this is a big deal. But will this actually happen? Can solid-state lithium metal batteries displace lithium-ion? Because we've seen how much the lithium-ion batteries have come down in cost. They're gaining a ton of momentum. So how could it actually displace lithium-ion batteries? Well, there has to be a big benefit of solid-state batteries, namely really high energy density. And this isn't just like a 5% or 10% improvement. It needs to be a step change, so 25, 30, 50% higher energy density to motivate this shift. The safety is a big one. If we don't have flammable liquid in there, it's a game changer. You don't have to worry about it. Even if you're in a collision and the battery's opened, it can be very safe. Reduced need for management systems, I talked about that. We can't sacrifice on cycle life. We still need that multiple 100,000-mile range. The difficult one, and I have these in red because they're definitely still works in progress. We need to be able to charge them comparatively at least as fast as lithium-ion batteries, preferably faster. And then we also need to make them at least competitively priced to lithium-ion batteries, which will involve establishing supply chain and a lot of things. And preferably, we would enable the use of existing production lines for lithium-ion batteries for these solid-state batteries, because, even in the last decade, there's been a huge investment by, all kinds of people and companies in these production facilities, so they're not easily going to just, abandon them. So where are we at in terms of these, requirements? We might be able to get there, but we need to kind of study the materials and understand them better. We need to know how they behave in an actual battery during fast charging, fast discharging, low temperatures. There's a lot of variables here. And then there's a lot of work that needs to be done in manufacturability. So in the interest of time, I'll just keep going. We've developed the solid state battery community have developed a large number of different candidate materials for the solid state electrolyte over the past 10 years. And each has their own strengths and weaknesses. None is really strong in every area. You have the sulfide materials here, which have very good conductivity, which means that the lithium ions can move back and forth very well, but they're not stable in air and they're not stable against lithium metal, which is a problem, but it's easy to process them. In contrast, you have these garnets, which are an oxide material. They are stable against lithium. They have a wide electrochemical stability window. They're air stable, but the conductivity isn't quite as high and they're not processable. So the game really becomes, well, which of these doesn't have an Achilles heel that can't be overcome? And it's interesting because if we look at the commercial space here, each company seems to be picking a different horse in this race. The Samsung paper that I just showed you, it uses a sulfide material called argyrodite. The Nissan and Toyota are using a different sulfide material. A startup company called QuantumScape, which if you've watched the stock market recently has really blown up and been very volatile, uses an oxide material that I think is one of these garnets. It's a bit hard to tell, but from the patent literature, it seems to be a garnet material. Another startup company is using a sulfide, and then you have several companies that are betting on polymer electrolytes because they're cheaper to manufacture. So we've come a long way. We've now developed ways to make these dense, thin film solid state electrolytes. We can make these small pouch cell type things, but I'll just jump ahead here. The question really isn't, can we make 10 or 100 cells? It's, can we make 10 or 100 million of them that all work and are all safe? That's a big question still. One thing that helps is when we're using lithium metal, actually all of the lithium can in theory come from the cathode rather than the anode, which means that you actually don't need to handle lithium metal when you manufacture the battery. You can make the cell without an anode and then just plate out a lithium metal anode on the current collector. So this basically removes a third of the manufacturing cost straight away because you don't have to manufacture an anode. Plus you don't have to work with lithium metal, which is very reactive, not stable in air, all kinds of problems. Yeah, almost done. So there's other challenges. So it turns out that solid electrolytes don't just inherently solve the dendrite problem. You can still get these lithium growths that penetrate into solid electrolytes because there are defects and things. And this is where that making 10 or 100 million becomes hard, because if one in every 10,000 has a defect, you might get a short circuit. Now, because it's a solid state battery, it's not going to catch on fire, but it will kill the battery, so it's not good. And then also during fast discharge, you might not strip the lithium uniformly, so you can get these voids, which cause issues as well. But despite these challenges, it really looks like this is the direction that electric vehicles are going to go in the not so distant future. So Volkswagen, so these are the top 5 automotive companies in the world, all of which are investing heavily in electric vehicles. Volkswagen has a very large solid state battery effort, says they're going to invest $86 billion by 2028 and have 70 full EV models by 2028 as well. Toyota, not quite as much money, although it's harder to find stuff. They say they're going to have at least 60 partial or full EVs by 2025, including at least one consumer model that has a solid state battery. They're going to debut a solid state battery powered vehicle at the Olympics this year. Daimler as well, huge investment, both consumer and they're big in commercial vehicles as well. Ford, not as big in the EV. They're kind of hedging their bets and sticking with a more diverse portfolio, but GM has a huge investment and also says they're going to stop producing internal combustion engines by 2035, which is, it really tells you that these big companies believe that electric vehicles are the future. And Tesla, you know, obviously is all electric, but they have not really shown interest in solid state. They think lithium-ion batteries are cheap enough that they're going to be the way to go for a long time. So many of these companies have now come out and said mid-2020s is really the time where they think it's going to switch from lithium-ion batteries to solid state because of this potential increase to go from 250 watt hours per kilogram up to, you know, 450 would be a huge game changer. And just in the past couple of months, there's been some really promising stuff from a couple of startup companies that are funded by these big auto companies. So Volkswagen has invested $300 million in QuantumScape in the past few years. And now just, you know, December 8th, QuantumScape released their first battery data and showed that this is a solid state battery, you know, in a small pouch shell that they can charge in less than 15 minutes at 30 degrees C, so approximately room temperature. Whereas, you know, like we just talked about, you might need, you know, even a Tesla needs 40 minutes or so to get 80% charge. So this is a big deal. And they also showed that they can cycle 800 times with a 1 hour charge and discharge, not the fast charge, but 1 hour charge and discharge, and still have well over 80% of the capacity. So this was a really promising release, and they're kind of in response to that. Another startup company that is sponsored by Ford and BMW put out this release about a week later, showing that they had these much bigger pouch cells that could be charged relatively quickly, can operate down to minus 10 C, et cetera. So this is the last slide. So I hope that I've convinced you that lithium-ion batteries are a really good option for both grid storage and EVs, and they're going to continue to get better and cheaper for at least the next few years, especially with a little bit higher energy density, and I think fast charging is coming. And that the future of EVs is really bright. I think, you know, we're at the inflection point. We're about to see a really dramatic change into what vehicles people are buying. I think in the next 5 years, it's going to shift from a majority not EVs to possibly even a majority EVs, because they're going to, in the next few years, probably by 2023, they're going to be cheaper than an equivalent internal combustion engine. They'll be cheaper to maintain and operate. They'll be longer lasting and more fun to drive. But if we're going to do that, obviously we're using electricity, so that electricity has to be accompanied, or the electricity has to come from renewable sources. So it needs to be accompanied by an expansion of renewable electricity production and a decrease in other energy demands, which requires a lot of grid storage. And finally, solid state batteries could be, this one's less certain, but it's looking positive for solid state batteries. They could be disruptive to the lithium ion market in the 5 to 10 year time frame, but there are still challenges. All right, that's all I have. Thank you for listening.
Thanks, that was a great talk. I learned a lot. There was one question by Josh Ambrose who had to run, but it's a good question, one which I was interested in also, which is the environmental impact of extracting lithium, and also if you do a life cycle analysis, what the net energy is. Yeah,
so they're both good questions. Actually, I might have a backup slide on the whoa, what happened? I lost my slides. There we go. Let me pull up here. So this is where the lithium reserves in the world are. So mostly not in the United States, mostly in South America. Bolivia and Chile have by far the biggest reserves. And the biggest source is lithium-based salts. So you're basically mining salt out of dried lake beds in Bolivia and Chile. So, and all of the projections that I've seen is that there is plenty of lithium in the world for this. It's not going to be particularly cheap ever to get at it, and there's not like a huge surplus, but there's enough to electrify the vehicle fleet and the grid for sure. And then at a certain point, we'll be able to rely on recycling of that lithium. That's a ways off, because if we're going to make battery electric vehicles that last 15 to 20 years, you're not going to have a large recycling, pool of old batteries to pull from for at least 15 to 20 years, hopefully. But at a certain point, you'll be able to recycle, and lithium's pretty recyclable from those batteries at this point, and solid state probably makes that better, actually. As far as the energy life cycle analysis, it's an interesting one. I read an article actually just today on this topic, or at least a related topic. And what I saw was that it may or may not make sense from a energy life cycle standpoint to have grid storage if we're using a lot of wind energy, because wind energy has a much quicker energy return on investment than solar. So that you have a more energy input to solar than wind. So wind energy, it might actually make more sense, rather than making more lithium-ion batteries to store wind energy, just turn the excess wind turbines. It's called, what is it called? Curtailment. Just stop producing electricity with those excess wind turbines and have more of them, because it's energetically, it makes more sense to build wind turbines than more batteries. So there is definitely a big cost, an energy cost for lithium-ion batteries. There's no doubt, but it's can be made much better than certainly burning fossil fuels from a life cycle standpoint, especially if we can use renewable energy to fabricate lithium-ion batteries.
Yeah, the one thing I've seen around curtailment is instead of curtailing those, whether it's wind or solar, when you have too much overbuilds, you don't need so much batteries, and then instead of curtailing, use that excess energy to like produce hydrogen and then use hydrogen as a storage mechanism, or use the hydrogen for industrial processes.
So it's an option. I think it probably, well, there are certain industrial processes where burning things makes more sense, because if you need really high temperatures, burning things makes more sense. But from kind of, as I showed at the beginning, hydrogen, it really is a storage vector, like you said, and is generally not as good as batteries in terms of efficiency and life cycle, because hydrogen, like electrolyzers and things, they use precious metals like platinum and things like that, which are very energy intensive.
I was talking about using hydrogen as a feedstock for processes, not as an energy source, not as industrial energy, but more.
Right. In order to make hydrogen, you have to use an electrolyzer, which has catalysts. Right. So you can, the two ways to make hydrogen are steam methane reformation, heat methane up really hot with steam. The hydrogen comes off, but that uses natural gas. It's not a good option for this. The other option is to split water, but it requires precious metal catalysts.
Oh, okay.
So for grid battery storage, would those also be lithium ion? So if we were to store on the electric grid, so for example, if we're using a lot of solar energy and wind energy, those are intermittently productive. So storage is extremely important. What is the feasibility of battery storage for electricity grids, and what are the best types of batteries for that?
Okay, here's my backup slide. It's not as cleaned up, but yeah, so the batteries are more expensive than pumped storage and possibly compressed air, but both of those are geographically constrained. You either need, for pumped storage, we talked about that, you need bodies of water at different elevations, or for compressed air, you need large underground caverns that are sealed. Neither is very widely distributed. So then after that, cost-wise, lithium-ion batteries becomes the next best choice. And lithium-ion batteries are coming down in terms of that.
So I just had a quick question on the first question that was asked. So, because when I talk to people about, electric cars, they all go to the very question that was started about the environmental impact oh, but you have to dig for the lithium, but do I would think, I don't know, that would be less damaging than coal or oil, going for oil to the environment, going for the lithium stuff, but I don't know for a fact if that's true.
Yes, I would say that is by almost any definition of impact, that is true. Mining lithium is not, it's not ideal, right? You're extracting something from the earth, and in this case it's not available locally, so we're gonna have to ship it around the world and all of that. But that's also true of coal, oil, and natural gas in most cases, and those processes tend to be more damaging to the environment. There are concerns with lithium. I have the same concerns, and I've read a lot of papers on this topic, that you have to use various chemicals in order to turn the lithium salts that are harvested into the useful feedstock for making these lithium-based materials and all of that. But, as I've said, my takeaway is that there is enough lithium, and it is a much better alternative to, as you say, the fossil fuels, which we are at now and desperately need to move away from. I think, climate change is the big thing. So, I hate to say this, but if you're reducing emissions, I think that's more important in the short term than having a mine on a dried lake bed.
So we're at 8:15 now. We're going to have to get to the rest of the agenda, so we're going to have to stop here. But thank you very much for your presentation. And